Okay, so today we're gonna learn the Lindstrom-Gessel-Viennot lemma. So this is a very beautiful and also very useful theorem. And but before stating this lemma, we need to introduce some terminologies. But there are basic terminologies in graph theory. So a graph is a pair of sets V and E, where E is a subset of V cross V Cartesian product with V, but empty set is not going to be there. Oh, sorry. No, so I think it's okay. So every element in V is called a vertex, and every element in E is called an edge. Okay, so basically a graph is object consisting of vertices and edges, where edge is a pair of two vertices. And sometimes when we say this, usually it's undirected, but if we say directed, G is directed. Oh, sorry. It means we treat UV different from VU as edges. And if we say undirected, then it means we treat these two edges the same. VU. Okay. So directed graph is a graph where these two are different. So these are kind of abstract notion, but if you think about the drawing of them, then it should be clear. For instance, this is a graph. This is a graph, our graph G, where the vertex set is 1, 2, 3. Edge set is 1, 2, 2, 3, 1, 3. Okay. So in this case, it's a directed graph. So when we draw a diagram for a directed graph, we use an edge like this. But if it's an undirected graph, we just an edge without this arrow. Okay. So in this case, a directed graph with 3 edges like that. All right. In this section, we will be considering directed graphs. Yeah, most of the time. Okay, let's see. And a path, say from U to V, is just a sequence of vertices. Say V0, V1, dot, 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 Vn, where such that the first vertex must be U, the last vertex must be V, is from U to V, and each adjacent vertices in the path must be an edge for all I from 0 to n-1. Okay. So in our example, in the previous example, maybe that's too simple, so let me draw something bigger. 1, 2, 3, 4, 5, 6. Maybe just I can draw something like this. Let's say the arrows go like that. Our directed graph looks like this, then say this is a path from 1 to 6. So P is 1, 2, 5, 6 is a path from 1 to 6, okay? Because first vertex is 1, last vertex is 6, and 1, 2 is an edge, directed edge in the graph, and 2, 5, and 5, 6, like that. And a cycle is a path from one vertex to itself for some u. Okay? So in this case, maybe I should give an example. Let me change this diagram a little bit so that we have a path to delete this. So in our example here, this is going to be a cycle. So example 1, 2, 5, 4, 1 is a cycle. And if there's no cycle in our graph, directed graph G, if G has no cycles, we say that G is acyclic. Acyclic means no cycle. So this is not acyclic because there's a cycle, but this is an acyclic graph because we don't have any cycle. The cycle must follow the edges in the direction of the edge. Okay. And I'm gonna use this notation. P of U to V is the set of all paths from U to V. Okay. Could be empty. Okay. And we also consider a weight on the edges. So a weight, an edge weight of G, which is a graph, directed graph, or directed or undirected, is just a function. It's just a function, which we write W e to, let's say, some commutative ring. So anything, it can be anything. Just you can think of this as Z or some polynomial ring or whatever. If there are parameters, it can be anything. So edge weight is just a way that we put some quantity at each edge. Okay. And let's see what else. And the weight of a path. Once we have a weight system, edge weight, then the weight of a path. P, say V0 Vn is defined to be W of P. It's just the product of all the edge weight. Okay, you just multiply the weight of each edge in that. Okay, so it's a bunch of definitions. And also, an n path is going to be just a sequence of n path. It's a sequence of n path. So we will write this boldface P, P1, Pn, where each Pi is a path. From any vertex to any vertex, we don't have any requirement on the starting and ending points of the edges or path. Okay, it can be any sequence of any n path. Let's see. Right, and an important concept today is whether paths are intersecting or not. So two paths, say P1 and P2, are intersecting. Intersecting means that they don't. They have a common vertex. Have at least one common vertex. And otherwise, it's not. Otherwise, they are non-intersecting. Okay, very natural definition, right? I'm going to show you some examples later. And also, we also say that n path p1 dot 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 pn is non-intersecting if they are mutually non-intersecting. Pi and pj are non-intersecting. For all ij, different of course. Okay, I think we have some more definitions. But you're almost there. Just a couple more definitions. Okay, now let's say G is a directed graph. With edge weight W, okay, and let's see, and let A the boldface A is a sequence of vertices, and B1 just be sequences of vertices. Okay, we just fix some n vertices and other n vertices like that. And P of boldface A to boldface B is the set of all n path. Say P1 dot 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 Pn such that Pi is a path from Ai to, but not necessarily Bi, but it's B sigma I for all I, and for some sigma permutation. Okay, that means A1 up to AN, they are starting points, and B1 up to Bn are ending points, but they can be anything. They don't have to, A1 doesn't have to go to B1 only, but you can go B1 or B2 or anything like that. But the ending point must all be distinct. That's because there's a permutation. Okay, so n vertex starting points can go anywhere to the n ending points as long as they are all distinct. Okay. And in this case, we define the sign of the n path to be the sign of the sigma, permutation sigma. So this tells us how we permute the ending points, basically. And also, weight of the n path is just a product of the weight of all paths. Finally, non-intersecting A to B is the set of all non-intersecting n path in this. So A's are the starting points, B's are the ending points, where the ending points can be permuted anyway. Okay, so yeah, this is all we need to state the Lindstrom-Gessel-Viennot lemma. Okay, yeah, we have stated a bunch of things, but all the definitions are quite natural, so it shouldn't be too difficult to memorize them all. But I will show you some examples, so yeah, you can see them later. Let's see. So let me state the theorem. This is called Lindstrom-Gessel-Viennot Lindstrom-Gessel-Viennot lemma. So for sure, sometimes it's called LGV lemma. Okay. So the statement looks like this. So G is a directed graph. Let's say acyclic. We don't want to consider cycle because acyclic. The reason why we don't want a cycle, because if there is a cycle, we will consider path from one vertex to another, but there will be infinitely many loops here. So there will be infinitely many a path from here to here. That we don't really want. So we can consider finite graph, no cycles, with edge weight W. Okay. And we fix two sequences of vertices. AN B equals B1 up to Bn. We fix this and then define M is defined to be the matrix, n by n matrix, where Mij is the generating function for all paths from Ai to Bj. And the weight is the weight of the path. Okay, so each entry looks like this. So each entry represents all the paths from Ai to Bj. Then the statement is about the determinant of this matrix. The determinant of this matrix is equal to sum over all non-intersecting n paths from the vertices A to the vertices B. Here we put the sign of the path, n path, and then we multiply the weight of that, like that. This is a statement. It's quite long, so I'm going to show you an example, because it seems quite complicated right now. Example. Before proving this, I'm going to show you why this is true for a simple example. Let's say G is this graph. These 9 vertices, like that, and edges are going always this way, okay? And this is A1, A2, and B1, B2. And let's just define the weight to be just 1, just we count path. Okay, then what is the matrix M? Is our Mij, ij from 1 to n. So M1, this is M11. What is M11? You consider all paths from A1 to B1. The weight is always 1, so you just count the number of paths from here to here. What is that? This is 1 step on the horizontal step, 2 vertical steps, so it's going to be 3 choose 1. 3, you have to choose 3 steps, and there is only 1 up step, so horizontal step, okay? And this is M12, so you go from A1 to B2. So there are 4 steps, then 2 horizontal steps among them, so 4 choose 2. And M21, so you go from here to B1. So 2 steps only and no horizontal steps, so it's like that. Finally, you go from here to here, so it's 3 choose 1. So the determinant of M is, let's compute the number. So this is 3, 6, 1, 3. So it's 9 minus 6 equals 3. So the determinant says is 3, but let's compute all the non-intersecting path from A's to B's. But if you consider them all, if you list them all, you will see that there are only 3 of them. Maybe I can use this. You go here, if you can go like that, and then like this. And also this, and this. So there are only 3 non-intersecting paths, and this always goes to the first vertex. This always goes to the second vertex. So the sigma here is always the identity map, identity permutation. So the sign is 1. So in this case, this is sign is always 1, and the number of non-intersecting lattice path is 3, exactly the one that we got from the determinant. Okay, so the theorem is true in this example, but instead of just computing them separately, we can actually compute the number of non-intersecting paths from this diagram. So let's compute. Instead of just listing all of them, let's try to compute all the non-intersecting lattice path using some kind of computation instead of listing them all. Note that any P in this example, P from A to B, P1 must go from A1 to B1, and P2 must go from A2 to B2, because if you go from A1, if you want to connect A1 to B2 and then A2 and B1, there must always be an intersection. So if you want a non-intersecting path, this should go there, this should go there. Okay? So in other words, non-intersecting path from A to B is a subset of this times right? So, but this is easy to compute. What is the cardinality of this? Cardinality of this is 3 choose 1. This is also 3 choose 1. So we just counted all two paths. A1, first path goes from A1 to B1, second path goes from A2 to B2. But of course, we counted too many. There will be some intersecting path. So we can just subtract the number of intersecting paths and we will get the right answer, okay? But how can you compute the number of intersecting paths? The idea is this is actually the crucial idea. This will be used in the proof of the Gessel-Viennot lemma, okay? To count let's count the number of intersecting paths. Two paths. P1 from A1, B1, P2, A2, B2. So like this. This is like this. The other path, say like this. Okay? P1, P2. Then because they are intersecting, there must be some intersection point, at least one. So in this case, we find first intersection. Say U. P1 and P2. So here is U is here. This is actually there's only one intersection in this case. And the idea is we change the tails of the path after U. So let P1, okay, let me divide this into two parts. P2 prime, P2 double prime, where this is before U, this is after U in the path. And similarly for this. Then we're going to define, say, Q1, P1 prime, and then P2 double prime, Q2, P2 prime, P1 double prime. In other words, basically a P1, P2 with the tails exchanged. Okay, so this becomes what? In this example, this becomes, so this, the tails are this and this. We change their tails, so they look like the blue one goes, it uses the tail of the red, so it goes like that, and this, it uses the tail of the blue, so it goes like that. So it changes things like that. And now let's consider them. Then what happens? Q1 is a path from A1 to B2 because the tail have been exchanged. This goes from A2 to B1. Okay? But now, just think about any such pair of paths. You go, if Q goes from A1 to B2, and if P2 goes from A2 to B1, they must intersect. They must always intersect because you cannot really go around this. So any such Q1, Q2 intersect. That means we can find the first intersection point, and then we can change their tails as well. Then we can do the tail exchange to get P1, P2 back, right? That means non-intersecting path here, intersecting path here are in bijection with a path from here. That means this gives a bijection from intersecting P1, P2, and this set. Right? But this one is easy to compute. What is the cardinality here? A1 goes from A1 from B2, so this is going to be 4 choose 2, and the other one is 2 0. So number of non-intersecting path is this number minus this number. So 3 1, 3 choose 1, 4 choose 2, 2 0. But if you think about it, this is exactly the determinant that we have before, like that. So we see in this determinant, if you expand the determinant, it has some structure here with some cancellation. So after the cancellation, we get just the number of non-intersecting lattice paths. This idea is basically the only idea, almost the crucial idea in the proof of the Gessel-Viennot lemma. We can use this to prove it. Okay, so let's prove the theorem now then. Proof of the theorem of the LGV lemma. All right. The determinant of M is by definition Mij, right? But what is the definition of the determinant? It's just sum over all permutations. You multiply the sign of the permutation and you multiply mi sigma I for all I from 1 to n. This is the definition of the determinant of a matrix. But we know this by definition is we define this to be the generating function for all paths from ai to b sigma I, weight of p. Yeah, this was the definition of Mij. Mij is like that. Okay. But if you look at this carefully, you will see that basically this means. Oh, sorry, I forgot to add this. If you think about it, yeah, let's just label it Pi. Then we have P1 Pn. Starting points are A's, ending points are B's. They're all ending points can be shuffled. A sign coming from the shuffling of the ending points. This is exactly sum over all n path from A to B, sign of P and weight of P. This is just the definition of n path. We just set up things so that this can be written nicely, simply in this way. So what do we want to do? So we want to show that this is equal. Is this equal to P non-intersecting path? The same thing. This is what we want to show. So this is a bigger set. We have a bigger set. We add all of these for the bigger set, but we want to show that for the smaller set, we add is enough to consider only the smaller sets. This is exactly of the form that we can use a sign reversing involution. We can define a sign reversing involution on this set with fixed points exactly this. Then we have a bigger set, a smaller set here, non-intersecting. The other will be all cancel each other. So we will be left with this. That's the idea. So enough to show. It is enough to show. Enough to find a sign reversing and weight preserving involution. Phi on the set P with fixed point set exactly this non-intersecting. Okay, this is what we want to do. This is our goal. Okay, so now we have all this set up. Proof is not that difficult and not that long, actually. So to find a sign reversing involution, let's consider an n path. P A to B. And let's say that maybe where Pi is a path from AI to B sigma I. Sigma is of course some permutation. All right. There are two cases. If P is non-intersecting, so we want to define what phi of P is. But we want this to be a fixed point, so of course this must be just P. If non-intersecting, just leave it there. Don't touch it. So suppose P is intersecting. This is the intersecting. This is the interesting case, right? What does intersecting end path mean? That means there is a pair in the path, in the end path, they are intersecting. So there could be several of them. So, but we can just find one of them. So find the lexicographically smallest. This is just one way to pick some intersection. There could be several ones, but this is we will just select it because it's lexicographically smallest. It's easy to find. Lexicographically smallest pair I comma j, such that pi and pj intersect. Yeah. If there are only two paths that are intersecting, then we can just pick them. But if there are many intersections, we have to pick one intersection. So this is how we select such an intersection. Pick the smallest ij. By the way, lexicographically smallest means that this is less than equal to say kl. Lexicographically means the first one is smaller, this is smaller than this, or if they are equal, this is smaller than this, and etc. So you compare the first element first, and then the next, etc. Okay, so we have now some intersection between pi and pj, and also there could be many intersections between the two paths, because path can intersect many times like that. So we have to pick one intersection, but we can just pick the first intersection. So let U be the first intersection point. Of pi and pj. So in the diagram is something like this. So pi goes from ai to b sigma I. It goes something like this, and b sigma j. Pj goes, maybe I should draw a little closer. Maybe just this and something like that. Okay, can you see this? Yeah. In this case, we have a 1-2 intersection. So just this is the first one. So this is going to be U. And the idea is the same. Do the tail exchange algorithm, does chain exchange thing. So here is, say, P I Q J, but we're gonna change. Maybe I can. Yeah. So this uses the tail of the PI. This uses tail like that. Okay. This is now say PI prime. This is QI. Sorry. Why is this QI? QJ. PJ prime like that. Define PI prime, PJ prime like that. Just changing the tails. And finally, phi of this end path, define this to be P1 dot dot dot. They're all the same, except the ith element becomes the Pi prime, jth path becomes Pj prime. The other ones don't change like that. Then what happens is, this is still a valid end path, but the sigma here, the way the ending points are connected is changing. Okay, before, okay, let's see. Let me explain this way. Note sigma, sorry, the sign of the original end path is sigma, sign of sigma. But what is the sign of the new end path? It's almost the same as sigma, but in sigma, so in the original path, the ith vertex is connected to sigma I, but now it's connected to sigma j, and this is connected to, this is of course a j. This is connected to sigma 2. So everything is the same except ij, their images are interchanging. So this is exactly the permutation that we can get by multiplying ij, the transposition ij. Because I goes to j and then j goes to sigma j, so this will send I to sigma j. And it will send sigma j to sigma I. But what is the sign of a product of two permutations? Product of their signs. But the sign of a transposition is always -1. So this is minus the sign of sigma. So it changes the sign. So the sign reversing. But is it weight preserving? Is this equal to this? And yes, this is of course yes, because what is the weight of a path? Product of weights of their edges. We have n path, bunch of path, and a bunch of edges. We change the path, but we never change the set of edges. Once there is an edge here, that edge is still there. It may belong to a different path, but they are all there. The set of edges with multiplicities are preserved, so this is true, because the set of edges used is preserved. So it's sign reversing. And it is an involution because phi is an involution. Because if you apply this, you will get p. So imagine that you have now phi of p. Then you now do the same algorithm. You find the path intersecting pi, pj, find the smallest ij, then it will still be the same. And also you will find this will be the first intersection points. You change the tails, then you get this. This is an involution. So it has all the properties we need: sign reversing, weight preserving, and involution. And the fixed point is exactly this. Where is it? Yeah, this. So that's basically it. That's the proof. We have everything we wanted. All right. So, by the way, this is a kind of general statement. The graph can be any directed acyclic graph. The edge weight can be anything. So we have kind of a very general abstract theorem. But most of the time we consider some special case. And one interesting special case is this corollary. G, directed graph. Edge weight W, and A is the sequence of vertices, another sequence of vertices, and M is defined the same way. I'm just writing the same thing, basically. Okay. And in this corollary, we have an additional condition. Suppose that every non-intersecting path, say P satisfies. So Pi is a path from Pi AI to some Bj, but must be always Bi for all I. That means the ith vertex starting point must be matched to the ith ending point. Suppose that we have that condition. Then determinant of the matrix M is the sum over all. This is the same non-intersecting path. But we don't have to worry about the sign. Just wait, because this means that the sigma is always identity, so the sign is 1. So we always have this. So actually this is really just a simple special case, but this is more commonly used. So in many situations we consider, in our example, many cases, there is only one sigma that makes these AIs to BJ's non-intersecting identity. All right. And of course, in particular, if the weight system, now the weight is always 1, then the determinant is just a number of non-intersecting lattice paths from A's to B's, where AI always goes to BI. Okay? That's a special case. Okay, I think we need some examples. Let me give you some examples. Examples. Yeah, we have one example here. This, okay, it's working. In this case, this is the special case that every non-intersecting path has the connecting pattern with a permutation identity permutation. But can you imagine the situation where the non-intersecting path has a different sigma, different connecting pattern? Yeah, there are cases like that. So let me show you. Just 3x3 grid. Think about this. Still goes edges going this direction. This we have A1, A2, B1, B2. If you think about it, then you will see that there are two different types of connecting patterns. So we can go this, or this, this, or this. They are non-intersecting, but this goes to 1 goes to 1, 2 goes to 2, or 1 goes to 2, 2 goes to 1. So it can be different. But let's compute the matrix M. What is the matrix M in this case? The determinant. So this entry is going to be the number of ways to, by the way, the weight is always 1. Number of path from A1 to B1, which is 4 choose 2. And what is 1, 2, 1, 2, so it's 6, choose 3. 2, 1, so it's 2 choose 1. 2, 2, so it's 4 choose 2. So actually we can compute this easily. This is 6, 22, 6. So 36 minus 40. So it's not even positive. So it's not, of course, the number of non-intersecting path, not number of non-intersecting path. But let's compute this in a different way in the right-hand side of the Gessel-Viennot lemma. So what is non-intersecting lattice path are there? How many non-intersecting paths are there? So if you maybe yeah, I don't think I listed them all. But if you think about it, just imagine that this goes to this, this goes to this. How many ways non-intersecting paths are there? Yeah, you have to avoid this. If you go this is the only way. And also, if you go this way, this is the only way. So in this case, there are 2. If sigma equals 1, 2, the identity, then number of path is 2. Okay? And what about sigma equals 2, 1 case? So we want to connect A1 to B2 and A2 to B1. But there are only 2 ways, so let's say you go this way. And how many ways are there that we can connect A1 and B2 without touching these points? We can go either one this way, 1, 2, or 3. And by symmetry, if you go this way, you can just multiply them 2. So in this case, number is 2, number of path is 6. So the Gessel-Viennot lemma says that right-hand side of the Gessel-Viennot lemma, Lindstrom-Gessel-Viennot, is sigma sine of 1, 2 times number of path 2 minus sine of 2, 1 number of path 6. This is 2. 2 minus 6 is minus 4. So it's the same as the computation. So. Yeah, there are a bunch of applications, but let me just tell you a little bit of remarks. Just a simple remark. What if AI equals AJ or BI equals BJ? What happens? So some vertices are the same. Initial starting points are the same. Then in the Gessel-Viennot lemma, this is sum over non-intersecting path, weight, O path, or sine of P, something like that. But this is empty. This is going to be empty because we have two paths have the same initial point, so this is going to be empty. That means that there's no sum in the sum, so it's a 0. But this can also be seen immediately from the definition of this. In this case, ith row and jth row must be the same because of the definition. The mi means MIL means you want to go from AI to BL. MJL means you want to go AJ to BL, but they are the same, so we are counting the same thing. We are considering the same path. So it's 0. So this is also seen to be 0 since row I equals row J. Similarly, in this case, column I, column J are the same, so it tells us that. Because of this, we don't really want to consider the case that these two are equal because it's just nothing. There's 0, 0. So we almost always we assume that AIs are all distinct, BJs are all distinct. But what about the case that what if maybe on the next page? AI equals bj for some ij. This gives us some non-trivial result, so it can happen. But then what is the path from AI to bj? Starting point is here, ending point is itself. So if you want to go from AI to bj, that's it. There's a stop. You stop there. So only one path, namely AI, which is just bj. But interesting thing is, consider other path like A1 is here, some BK is there. This can go, but this should not touch this if you want a non-intersecting path, right? So in this case, all other path in a non-intersecting intersecting path, in the non-intersecting lattice path, non-intersecting path from A to B, must avoid AI, this point AI. It must go somewhere other than this. It must not touch that. And because of this, we can actually find a number of paths. We have a bunch of stuff there. So we want to count number of paths from here to here, avoiding a bunch of given list of points. We can do that using this idea. That will be one of the homework problems. Okay, and let me give you some more examples. Example. Oh yeah. Let's say G is a directed graph with vertex set is just a A1, AN, B1, BN. And edge set is just AI to BJ for all IJ. So basically it looks like this. A1, A2, dot, 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 AN. B1, B2, dot, 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 BN. You just connect them all. Okay. And let's see. And what is this? AI to, oh, of course, the direction is always this way because AI equals from AI to BJ. What is this step? We want to go, say, A1 to, say, B3. There's only one path, using only one edge. So this is just AI, BJ. Okay? So in our matrix M, generating function for the Mij. What is Mij? Generating function for all lattice path, all path from AI to Bj with a edge weight. But there's only one path with only one edge. So this is going to be this, and what is the weight? Is just the weight of AI Bj. Okay? In this case. And what does this mean? What does the LGB lemma tell us? P, all non-intersecting path from A's to B's, sign of P, weight of P. But What are the non-intersecting paths here from A's to B's? For instance, let's just consider the simple example, like, yeah, maybe example, maybe n equals 2 case. We can go either this way or this way, right? This is non-intersecting. This is intersecting, right? Intersecting. Is this intersecting? Is this an intersecting path? What is the definition of intersecting end path? Two paths are intersecting if they share a common vertex. But this is non-intersecting because this is not a vertex. This is just an illusion that looks like a vertex, but this is not. Every end path is non-intersecting here, right? So every P is non-intersecting. Because no matter how two paths you choose, as long as their initial and ending points are different, these initial and ending points are the only vertices appearing in their path. So they are non-intersecting, right? So it doesn't matter. So you basically consider all paths, all end paths there. But what does that mean? That means, so this can be rewritten we can rewrite this just like this. So all paths, doesn't matter, because everything is just non-intersecting. But let me rewrite this. Yeah, this means the ending points can be permitted in any way. We have the sign, and then all path here from AI to B sigma I, there's only one path with only one edge. So this is exactly the weight of one path AI to B sigma I, right? But what is this? This is just Mij, Mi sigma I. So this is just the definition of the matrix, the determinant of a matrix. So we didn't do anything. So in this case, the Gessel-Viennot lemma doesn't give you any new information because it's just the same, it tells us the same thing. But the interesting thing is this can be used to prove a very useful theorem called the Cauchy-Binet theorem. This means that we can somehow give some combinatorial meaning to a determinant. So for any, this means that any determinant has some kind of combinatorial meaning. Because just let's say, for instance, m equals, I don't know, 1, 2, 3, 4. Then the determinant of m has a combinatorial meaning. I mean, this way. So 1, 2. It's a little confusing, so let's say A, B, C, D. So this, we have edges like that. I'm going to label 1, 1. Yeah, I think it's A1, A2, B1, B2. A1 to B1, I'm going to label it A. A1 to B2, I'm going to label it B. And this is C and D. Then this, the determinant of this is the generating function for all non-intersecting paths here. So we can give some meaning. So this can be used to prove Cauchy-Binet theorem that is quite also quite useful theorem in linear algebra and yeah. Yeah, I'm not sure I have enough time, but let me just define just I think I can state the theorem at least. So we have a matrix M, any matrix. Let's say their indices are in the set of integers 1 up to n. Oh, sorry, it can be any, not necessarily a square matrix. Any matrix, n by n. And let's say I is a subset of M, J is a subset of N. Oh, sorry. Yeah, I think I need to introduce one more. Sorry. So M choose K. So this is a set. This is an integer, a negative integer. This means the set of all subsets of M with cardinality K. That's notation in mathematics. So for a subset of M with cardinality K, and for a subset J of N with cardinality K, so that they have the same cardinality, the IJ minor of the matrix M is denoted by bracket M with I comma J. This is just a number, like a determinant of Mij, but I is in the chosen indices index set I, J is in the chosen index set B. This is called a minor. So for example, in this example, yeah, it's too simple, but yeah, maybe it's too simple. M equals A, B, C, D, E, F, G, H, I. And the minor of the I is like 1, 3, say 2, 3. You just select row, first and third rows, and second and third column. So that's going to be, yeah, so this, B, C, H, I. That's the minor. All right, I think we can state the theorem. It's called the Cauchy-Binet theorem. So let's say M is an N by L matrix, and N is an L by N matrix. Okay. Then, so they are not square matrices, not necessarily square matrices, so we cannot define the determinant of M. But their product is N by N. So we can consider the determinant of their product, Mn. This is equal to sum over all I subsets, N subsets, subsets of L of cardinality N, M, N, I, maybe I need more space, N minor I, N. This is what's called the Cauchy-Binet theorem. Yeah, it's a quite useful theorem, and we can prove this using just the Lindstrom-Gessel-Viennot lemma, using this trivial identity. The idea is we kind of build graphs so that this is the Gessel-Viennot lemma left-hand side, and this becomes the Gessel-Viennot lemma right-hand side. And they are equal. That's how we prove it. I'm going to show you the proof in the next lecture. Okay, I will stop here. Thank you for your attention.